This research is a complete study on the process of controlling the power of devices operating on alternating current AC, using the method called phase control. And examples of these devices are heaters, motors, lighting devices of medium or high electrical power. We have prepared this research in a simplified manner, in which we dealt with the main ideas of the project in a logical sequence, step by step. Therefore, we recommend following this research from the beginning without going beyond any stage, so that you have a complete idea of what does phase control mean, and how to design and program the components of the electronic circuit correctly. The main elements of the project. TRIAC is the heart of the project, and the main control element in the phase control process. In this study, we used the TRIAC BTA16 and microchip 16F877A microcontroller. We assume here that you have sufficient experience with microcontrollers. Of course, you can use any other equivalent elements. For example, you may use the Arduino instead of microcontroller. But first of all, you need to understand the idea in theory, then the practical application will be possible and easy in any way. Now, let's begin with the most important component in phase control project, which is the TRIAC. TRIAC is an electronic element that has 3 pins, T1, T2, and G. These pins are often located as in the figure, but it is necessary to verify the pin diagram from the data sheet. This shape is the symbol of the TRIAC. Sometimes, it's referred to T1, T2 as MT1, MT2 or A1, A2, respectively. In general, we can look to the TRIAC as an on-off switch, where T1, T2 are its terminals. We can control the state of T1, T2 by applying an electrical signal on the gate, pin G. This signal is called gate triggering signal, which we will learn about shortly. Therefore, the TRIAC is described as an electrical switch, used for controlling the operation of electrical devices, by controlling the state of one of the power lines, as shown in the figure. Now, let us talk about gate triggering signal. The TRIAC is triggered by applying an electrical voltage Vg on its gate. This will cause an electrical current Ig to flow in the gate. In order for the triggering signal to be effective and safe, 2 things must be taken into account. First, the value of Vg must be equal to a value called VGT, gate threshold voltage, at least. Second, the value of the electric current Ig flowing in the gate must be adjusted so that it does not exceed the maximum allowed value of IGT. These 2 values, VGT and IGT, are mentioned in the data sheet of the TRIAC, provided by the manufacturer, often in the table of electrical characteristics. Here are these values for TRIAC BTA16-600B, used in this project. VGT equals 1.5 volts. IGT equals 100 mA. Note that a 100 mA for IGT is the maximum value allowed for Ig. As we see, the values of VGT and IGT are very low, therefore the triggering signal is described as a low-power electrical signal, and it can be easily generated using any I/O pin of the microcontroller. Let's assign pin A0 to trigger the TRIAC. Of course, we have to configure this pin to be an output. From A0 output pin, we can get a 5-volt signal, and this is suitable value for Vg. Also, we can draw an electric current up to 200 mA, based on the microcontroller specifications mentioned in the data sheet provided by Microchip. But, since that the gate current, Ig, should not exceed the maximum value of IGT, which equals to 100 mA. it is necessary to use a resistor to limit the value of the gate current, Ig. The value of this resistor can be easily calculated from Ohm's law. A resistor of about 47 ohms will be suitable. We would like to refer that at low temperatures, the Ig and Vg values of the triggering signal should be slightly higher than the values specified in the datasheet. Therefore, it is okay to increase these values by 15 to 20%, in anticipation of a decrease in temperature. Finally, this is the circuit for driving the TRIAC using the microcontroller. The TRIAC is triggered by sending the logic 1 to the gate from a 0 output. The TRIAC now is on, and the load works. By sending logic 0, the TRIAC returns to off state. But for this circuit to work, one last procedure is required. This is TRIAC triggering circuit using DC current provided by microcontroller. In this circuit, there are two different sources of power supply. The 5-volt DC power supply, for electronic circuit elements, and the 220-volt AC, 50 Hz power supply, for powering the device. The microcontroller triggers the TRIAC with a positive pulse on the gate. The new information now is that the triggering current Ig flows through the gate and terminal T1. The source of the triggering current is the DC power supply, so, for the triggering current Ig to flow through the gate and the terminal T1, it is necessary to close its path in the DC power supply, where the triggering current comes from. As the triggering current is positive on the gate, we have to connect the terminal T1 to the ground of DC power supply. Note that we have to connect T1 to the positive line of the DC power supply if the triggering current is negative, and this is also possible. However, in this research, positive current Ig is used. Now, this is the last diagram of the triggering circuit after the connection between the terminal T1 of the TRIAC and the ground of the 5-volt DC power supply. Although this circuit works and the TRIAC is triggered fine, but it's not ideal, and could be dangerous. The disadvantage of this circuit is exactly this connection between the terminal T1 and the ground of the 5-volt DC power supply, which results in a direct connection between the 5-volt DC power source and the high-voltage 220-volt AC power source. This direct wired connection between two power sources, operating at two extremely different voltage levels, 5-volt DC and 220-volt AC, is very dangerous, especially when working with high power loads, where voltage and current levels may reach high values, and may cause a critical damage of the electronic circuit components. To get rid of this problem, it is necessary to isolate these two power sources, without having any wired connection between them. For this purpose, many manufacturers have created an electronic component, called an optoisolator, or optocoupler. Let us now talk about this wonderful element, the optoisolator. The optoisolator is an electronic element, in a form of integrated circuit. It works as a TRIAC driver, used to trigger the TRIAC in an active and safe way. And examples of isolators are MOC32X and MOC36X. They all share the same main task, as a TRIAC driver, and differ in some characteristics. In this project, MOC3023 optoisolator is used, so, let us start with a brief description about this IC. MOC3023 optoisolator is a 6-pins integrated circuit. Consists of two parts. The input part, which is an IR LED, where pins 1 and 2 are its positive and negative terminals respectively. The output part is a photodiac, where pins 4 and 6 are its terminals. The pins 3 and 5 are not used. This element, works in a very simple way as follows. When electric current flows through the IR LED, it emits an infrared light, the TRIAC responds to the emitted light signal, and triggers the TRIAC. Now, let's modify the previous triggering circuit by adding this optoisolator. The output pin A0 of the microcontroller will be connected to the positive terminal of the LED, pin 1, where the negative terminal of the LED, pin 2, must be connected to ground. To turn on the LED, the microcontroller sends logic 1 through A0 output pin. This means, applying 5 volts DC on the positive terminal of the LED, this causes an electric current to flow, causing IR light to be emitted from the LED. The TRIAC in the output part receives the light signal and triggers the TRIAC. Therefore, the TRIAC should be connected to the TRIAC gate, pin G. This is the connection diagram as mentioned in the data sheet of the optoisolator MOC3023. But, for the optoisolator to function properly, two parameters must be taken into account. The first parameter is LED trigger current, referred to as IFT. It is the value of the electric current that must flow through the LED, for the TRIAC to respond to the emitted light signal. Second, LED forward current, referred to as IF. It is the maximum value of the electric current allowed to flow through the IR LED. The values of IFT and IF are mentioned in the data sheet of the optoisolator. For MOC3023, these two values are IFT equals 5 mA at 3 volts on the LED. IF equals 60 mA. Note that, the most appropriate choice for the value of the IR LED current, is the average value between IF and IFT. It is the value recommended by the manufacturer, as mentioned in the data sheet of the optoisolator. The average value between the two values, IFT, 5 mA, and IF, 60 mA, is 32.5 mA. To adjust the value of the LED current, to be as close as possible to this value, a resistor must be added in series with the IR LED as in the figure. We can easily calculate the resistor's value, using Ohm's law. The 5 volts from A0 is divided into 3 volts on the LED, 2 volts on the resistor. For a current of 32.5 mA, the resistor is about 60 ohm. The optoisolator now is ready to trigger the TRIAC as per the logical signal sent by the microcontroller. When the microcontroller sends logic 1 through A0 output pin, the optoisolator triggers the TRIAC, and vice versa. In this schematic, the IR LED draws a current of about 32.5 mA from the microcontroller directly, through A0 pin. Although the microcontroller can supply a current up to 200 mA through any of its I/O terminals. But it is always better to avoid drawing high electric current from the microcontroller, so, it's recommended to power the LED using a transistor. Now, instead of drawing 32.5 mA from the microcontroller, the transistor just needs a few microampere on its base, to get connected and turn on the LED which draws its current from the main power supply. This is a good improvement over the triggering circuit, however is not necessary. Besides the aforementioned improvement over the input part of the optoisolator, a few other improvements and additions over the output part responsible for triggering the TRIAC, are also recommended, and sometimes are necessary. Some of these improvements are related to the optoisolator, others, to the TRIAC characteristics and specifications. Here are a brief description of the most important of these improvements. First, adding a resistor between the gate and the terminal T1 of the TRIAC. This resistor reduces the sensitivity of the TRIAC gate and minimize the effects of external noise, that may sometimes cause flowing an unwanted electric current through the gate, which ends in triggering the TRIAC at a wrong time. The recommended value for this resistor is 360 ohms. Note that, using a certain types of TRIACs, such as H-type, like BTA16-600H, this resistor can be neglected, because it has a less sensitive gate, and better resistance against the effects of noise. Second, using a snubber circuit, that consists of a resistor and a capacitor in series, connected in parallel, between the two terminals of the TRIAC, T1 and T2. Snubber circuit is a braking circuit that assures and confirms the disconnection of the TRIAC when the AC electric current of the device reaches the 0 point, with the absence of the gate triggering signal. We will talk about this circuit in detail at the end of this research. The practical values of the elements in the snubber circuit are a resistor of 39 ohm, 1 watt, or a little more. A capacitor of 100 nanofarad, 400 volts. Finally, for safety purposes, it is recommended to use electrical protection elements at the 220 volt AC input, such as varistor and fuse, with appropriate values. Now, let's take a look at the sine wave of AC, voltage, and current. For the following topics to be clear, we will assume that the device we want to control using the TRIAC is a lighting device, with the following specifications. Supply voltage is 220 volt AC, 50 Hz. The power of the device is 1100 watt. This device will be used as a practical example in all topics of this research. According to the power law, electric power is voltage multiplied by current. So the current drawn by the device is 1100 watt divided by 220 volt, equals 5 ampere. When the TRIAC is triggered by sending 1 through a 0 output pin of the microcontroller, the device is connected to the electrical supply 220 volt, the current of 5 ampere flows in the device through the terminals of the TRIAC, T1 and T2. Let's take a look at the AC voltage and current waves. We assume that the device is connected to the electrical power at the 0 point of the voltage wave. As soon as the device is connected, the voltage gradually increases from 0 to the maximum value 220 volts, then it decreases from the maximum value to 0. This is the positive pulse of the AC voltage wave. The process is now repeated in the same manner, but in the opposite direction. The voltage increases from 0 to the maximum value, then decreases to 0. And this is the negative pulse of the AC voltage wave. Both the positive and negative pulses form a sine wave voltage. Of course, the higher the voltage, the higher the current and the higher the power. This is according to Ohm's law, voltage equals current multiplied by resistance. And Power's law, power equals current multiplied by voltage. At 0 point, in the beginning of the wave, the voltage is 0, therefore, the current and the power are also 0. At this point, the device is in off state as if it is disconnected from the electrical supply. As the voltage increases, the current flowing in the device also increases, and so does the power. And when the voltage reaches the maximum value of 220 volt at the peak of the pulse, the current is maximum and equals 5 amperes. The device now operates at the maximum power of 1100 watts. From this point, where the voltage, current, and power are at their maximum values, the voltage begins to decrease, and of course, the current and power will decrease as well. When the voltage reaches 0, the current and the power become 0. At this point, the device is in off state again as if it is disconnected from the electrical supply. Again, the process is repeated in the same manner, but in the opposite direction. From zero value for voltage, current, and power, to the maximum values for each, then decrease to zero. Let's ignore the voltage wave, this is the sine wave of electric current. Based on the previous information, this AC current flows in the device through the triac, after triggering the triac by sending one from a zero output pin of the microcontroller, and keeps flowing as long as the triggering signal is present, that is, as long as a zero output pin of the microcontroller equals 1. When the microcontroller sends 0, the triggering signal is removed, the triac is switched off, and the device is disconnected. Although this description is correct, but it is not accurate. In fact, the triac is not so simple to be just an on-off switch. This element behaves in a distinctive way when an AC current passes through it. This behavior is the result of two important features of the triac. These two features are the basis of the process of controlling the power of electrical devices. Let's learn about these two features. The first feature is the on-state feature. When the current reaches a value called latching current, referred to as IL, the triac becomes conductive regardless of the triggering signal, whether it is present or not. By other words, when the triac is triggered by sending one from the A0 pin of the microcontroller, it switches on, and the device is connected to supply voltage, 220 volt AC, assuming at 0 point, the current now begins flowing in the device through the terminals, T1 and T2 of the triac, so, the triac senses the changes the current is going through. As mentioned earlier, the current increases gradually with the sinusoidal curve from 0 towards the maximum value, 5 ampere. When the current reaches the value of IL, the triac becomes conductive, even after removing the triggering signal. This means that after the latching current, we can remove the triggering signal by sending 0 from the microcontroller, while keeping the triac and the device connected. The value of latch current, IL, is mentioned in the data sheet of the triac. For triac BTA16-600B, the latching current is within the range, 40 to 70 mA, as per the triggering point. For safety, consider the bigger value of 70 mA. We would like to say that in general, the latching current, IL, has a much lower value compared to the device current. For example, our device of the medium power, 1100 watt, draws a current of 5 ampere, this current is much higher than the latching current of only 70 mA. It seems clear that the device current that will increase up to 5 ampere, reaches immediately to the value of latching current, 70 mA. Meaning that the triac becomes conductive, within a very short time after it has been triggered. At this moment, we can remove the triggering signal, while keeping the triac connected. We can say that, the triggering signal after the latching current, is useless. That was the first feature called, on-state. Now let's move on to the second feature. The second feature is, the off-state feature. After the current reaches the maximum value, it will start decreasing gradually towards 0, when the current reaches a value called, holding current, referred to as, IH, with the absence of the triggering signal, the triac switched off, and the device is disconnected. By other words, after the current drops to IH, the triac behaves in one of the following two ways. First, if the triggering signal is present, that the microcontroller output pin A0 equals 1, the triac remains conductive, so, the device remains connected and keeps working. Second, if the triggering signal is not present, that the microcontroller output pin A0 equals 0, the TRIAC switch is off and the device is disconnected. The value of holding current, IH, is mentioned in the data sheet of the TRIAC. For TRIAC BTA16-600B, the holding current is 50 mA. Note that IH value is near the IL and close to zero. It is clear that in every half wave of electric current, positive or negative, the TRIAC passes through the two states. The on state, when the current rises to the value of IL, while increasing from 0 towards the maximum value. The off state, when the current drops to the value of IH, while decreasing from the maximum value towards 0. From on state to off state, the TRIAC is always conductive whether the triggering signal is present or not, but after the off state, if the triggering signal is present, the TRIAC keeps conductive, and vice versa. Let us now ask the following question. What will happen when triggering the TRIAC only once, assuming at 0 point? Of course, to trigger the TRIAC once, the microcontroller must send 1 for a short time, and then send 0 immediately. But before answering the question, it is necessary to know, for how long time the microcontroller should send the 1, so as to ensure that the TRIAC is triggered successfully, before sending 0 to remove the triggering signal. Here is the answer in short. To ensure that the TRIAC will be triggered successfully, the microcontroller must send 1 for at least 200 microseconds or a little more. The value of 225 microseconds is ideal, practical and tested. So, in order to trigger the TRIAC only once, the microcontroller sends the 1 for 225 microseconds, then sends the 0 immediately. Now, here's what will happen when triggering the TRIAC at 0 point just once. The current increases from 0, when it reaches the value of IL, 70 mA, the TRIAC enters the on state. It is now conductive in spite of the microcontroller output A0 equals 0 and the triggering signal is not present. The current continues to increase until it reaches the maximum value of 5 ampere, then begins decreasing towards 0. When it reaches the value of IH, 50 mA, the TRIAC enters the off state. Of course, it will switch off because the triggering signal is not present. So, the device disconnects and stops operating. The result is, by triggering the TRIAC just once, the device operates for most of the half-wave time, which means, for about 10 milliseconds. This is of course, when working at a frequency of 50 Hz of the AC current, that means, 50 full waves, or 100 half waves per second, so the half-wave time is 10 milliseconds. Now, let's take a closer look at the half-wave of the AC current. As mentioned, the half-wave time is 10 milliseconds, it is the time between two consecutive 0 points, Z1 and Z2. In the previous example, the microcontroller triggered the TRIAC once at the 0 point, Z1, in the beginning of the half-wave. The result was that the TRIAC switched on for most of the half-wave. It can be said that, the device operated for the entire half-wave. Now, let's see what happens when the TRIAC is triggered somewhere beyond the 0 point, let it be at point A1, 1 millisecond after the 0 point. As the microcontroller triggers the TRIAC at point A1 just once, by sending the 1 for 225 microseconds followed by 0. The TRIAC switches on and enters the on state, during which, it remains conductive despite the absence of the triggering signal. Of course, the device is connected to the electrical supply immediately when the TRIAC is triggered, that is at point A1. The current flows in the device from point A1, until it reaches the value of the holding current IH that is close to 0, where the TRIAC enters the off state, and of course, switches off due to the absence of the triggering signal. It seems clear that from the beginning of this half-wave, Z1, to point A1, the device is disconnected, while it is connected from point A1 at which the TRIAC was triggered, to the end of the half wave Z2. That is, the device during this half wave will be off for 1 millisecond, and on for 9 milliseconds. Now, it is easy to know how to operate the device for a specific period during of the half wave time of 10 milliseconds. Let it be for the half of the wave time, which means, for 5 milliseconds. Simply, the microcontroller must trigger the TRIAC just once in the middle of the half wave at the peak point, A5. The device now will work for only 5 milliseconds, from point A5, to the end of the half wave at the point Z2. In this way, we can control the operating time of the device during the half wave time, that is, by controlling the timing of the TRIAC's triggering. Now, we have most of the necessary information to start with the main topic of this research, controlling the power of electrical devices. Let's begin. The process of controlling the power depends on the idea of controlling the operating time of the device within each half wave of the electric current, as previously mentioned. At a frequency of 50 Hz, the time of the half wave is 10 milliseconds. When the TRIAC is triggered at the 0 point in the beginning of the half wave, the device operates for almost the entire half wave, meaning that the device works at its maximum power. The longer the TRIAC's triggering time is delayed from the 0 point, the shorter the operating time of the device, and the lower the power. As we mentioned earlier, the TRIAC is triggered by the microcontroller and the OPTOISOLATOR. The microcontroller issues the triggering command by sending one from a 0 output pin to the OPTOISOLATOR, which responds immediately and triggers the TRIAC. The OPTOISOLATOR, MOC3023, triggers the TRIAC randomly. That is, without knowing, or caring, at which point in the half wave the triggering occurred. What we want to say is that, the microcontroller is responsible for issuing the command to the OPTOISOLATOR in the correct position of the half wave, at which it wants to trigger the TRIAC. For the microcontroller to be able to do this, it must be able to know when the half wave starts, so that it can decide for how long time it must wait to reach the point at which the triggering command must be issued to the OPTOISOLATOR. Each half wave starts at the 0 point and ends after 10 milliseconds at the next 0 point, so the microcontroller should be able to detect the zero crossing points of the AC current wave. This is our next topic. In this topic, we will see how the microcontroller can detect 0 points of the AC current wave. The microcontroller is an electronic digital device, whose operating voltage is 5 volts DC, so, it cannot be connected directly to the 220 volts AC power lines. For the microcontroller to detect zero crossing points, we must first detect these points somehow, then, convert them into digital pulses that the microcontroller can understand. For the first step, we will use a simple and effective zero-cross detection circuit, consisting of only two components, a full-wave rectifier, and an optocoupler with a phototransistor-based output. The rectifier converts the input alternating current, AC, to output direct current, DC. The full-wave rectifier converts each AC half-wave into a DC pulse, as in the figure. The rectifier output is not a pure DC signal because there is no smoothing capacitor, it is just a pulsating DC signal, where each pulse represents a half-wave of the AC current wave. The second component in the circuit is the optocoupler, 4N28. Similar to the OPTOISOLATOR, MOC3023, used earlier to drive the TRIAC, the optocoupler, 4N28, is a 6-pins integrated circuit, consisting of two parts. The input part is an IR LED, where pins 1 and 2 are its positive and negative terminals respectively. The output part is NPN phototransistor, where pins 4 and 5 are the emitter and collector respectively. Pin 3 is not used. Pin 6 is the base of the phototransistor. It is also not used in this circuit. This element works in a simple way as follows. When an electric current flows through the LED, it turns on and emits an infrared light. The phototransistor becomes conductive, that is, a connection occurs between its terminals, emitter and collector. When the LED turns off, the phototransistor disconnects. This is the practical circuit of the optocoupler, 4N28. The emitter, pin 4, is connected to ground, where the collector, pin 5, is pulled high to 5 volts using a pull-up resistor. When the LED is off, the transistor is also off, so, the output of the optocoupler is 1 due to the pull-up resistor. When the current flows in the LED, it turns on, the transistor becomes conductive, so, the output is 0. Here is the zero crossing detection circuit using the full wave rectifier and the optocoupler, 4N28. The positive and negative outputs of the rectifier are connected to the positive and negative terminals of the LED respectively. It is necessary to use 2 resistors in series on both ends of the LED to limit the current. We can use 1 equivalent resistor, but 2 resistors is more efficient for heat dissipation. The values of the resistors are easily calculated from Ohm's law. This is of course, after knowing the LED current from the data sheet of the optocoupler. As mentioned earlier, the output of the rectifier is not a pure DC, it is a pulsating DC signal, where each pulse represents a half wave of the AC input wave. These DC pulses flow through the LED lights up at most of each pulse, with the transistor is connected, and the output is 0. When the pulse reaches 0 or very close to 0, the LED turns off, the transistor disconnects, and the output changes to 1. As soon as the next pulse starts in a very short time after the 0 point, the LED lights up again, the transistor switches back on, and the output changes to 0, and so on. It seems clear that at each 0 point, a logical pulse occurs at the output of the optocoupler, during which, the output changes from 0 to 1, and back to 0. In this way, the 0 crossing points of the AC current wave are converted into logical pulses that the microcontroller can read and understand. All that is required now, is to connect the output of the optocoupler to one of the input-output pins of the microcontroller, then, configure this pin as input. The microcontroller can now easily detect 0 crossing points, by detecting the changes at its input. But, the best way to detect changes, is to use the interrupt. The use of the interrupt varies depending on the microcontroller used. The microcontroller 16F877A supports several forms of interrupt, including the external interrupt on pin B0 of the port B, referred to as RB0 interrupt. This interrupt is edge-triggered, either by rising or falling edge at pin B0. The edge is selected optionally in the interrupt registers of the microcontroller's memory. To use the RB0 interrupt, we have to connect the output of the optocoupler to the pin B0 of the microcontroller. Zero cross detection circuit is now complete. Let us modify the previous TRIAC driving circuit, by adding the zero cross detection circuit. This is the final form of the electronic circuit diagram used to control the power of the electrical devices. All we need now, is to program the microcontroller with the appropriate code, through which we can control the timing of the triacs triggering in each half wave, which means, controlling the operating time of the device within each half wave, and thus, controlling the device's power. The process of controlling the power will be simple and clear through the following example. In this example, we'll set the device's operating time in each half wave, so that it is on, for 6 milliseconds, and off, for 4 milliseconds. In the power control circuit, pin A0 of the microcontroller is used to trigger the TRIAC. Therefore, A0 pin must be configured as an output, with an initial value of 0, to confirm that the TRIAC and so the device are disconnected at startup. RB0 interrupt is used to detect zero crossing points. As explained earlier, at 0 point or very close to 0, the output of the optocoupler changes from 0 to 1. This means that a rising edge occurs at pin B0 connected to the optocoupler's output. So, B0 pin must be configured as an input because it reads the state. The next important step is to configure the interrupt so that it occurs at the rising edge at pin B0, which means, at 0 crossing points. After completing the preceding steps, we just have to enable the interrupt, and the microcontroller will start executing the code of the interrupt procedure every time the interrupt occurs, that is, at every 0 crossing point. Let's take a look at this code. This code was written in MicroBasic language, using the Microelectronica IDE. The microcontroller starts executing the code from the main statement line. The first command is to enable the global interrupt by setting the bit GIE in the interrupt control register. The microcontroller 16F877A supports many forms of interrupts. Setting GIE bit enables all interrupts. Individual interrupts can then be enabled or disabled by their corresponding bits. The next command is to disable the RB0 interrupt. RB0 interrupt can be enabled or disabled by setting or clearing the INTE bit in interrupt control register. We will disable this interrupt initially, until the main settings in the following lines are finished. In the next command, we set the bit INTEDG. This bit is the interrupt edge select bit. Setting this bit means that the interrupt is at the rising edge on RB0. The next command is to disable the analog to digital converter. This is to configure all pins of port A as digital I/O pins. The next two commands are to configure A0 pin as output, and set the initial value of A0 to 0, this is to confirm that the TRIAC is disconnected at startup. The next command is to configure B0 pin as input. The next command is to enable the RB0 interrupt by setting the bit INTE in the interrupt control register. The last two commands are an endless loop, in which the microcontroller does nothing but wait. The interrupt is now enabled. The microcontroller responds to the first interrupt that occurs at the first 0 crossing point, Z1, where it goes immediately to execute the code of the interrupt procedure, in which the microcontroller should trigger the TRIAC just once after 4 milliseconds. Let's add the interrupt procedure code the microcontroller should execute at each 0 crossing point. In the first line, the microcontroller delays for 4 milliseconds, with the TRIAC is already disconnected and the device is switched off. In the next 3 lines, the microcontroller triggers the TRIAC just once, by sending one from A0 pin for 225 microseconds, followed by 0 to remove the triggering signal. The last command is to clear the interrupt flag bit, INTF, in the interrupt control register, and leave the interrupt procedure. The microcontroller sets this bit every time an interrupt occurs. This bit must be cleared in the code to exit the interrupt. When leaving the interrupt, the microcontroller returns to the place it was in when the interrupt occurred, which means, to the endless loop. By triggering the TRIAC once in the interrupt procedure, the device works for 6 microseconds, from the triggering point to the end of the half wave, where the TRIAC enters the off state and disconnects immediately due to absence of the triggering signal. The next interrupt occurs at the next 0 point, Z2, with the device is already disconnected. Again, the microcontroller goes to execute the interrupt procedure, where it waits 4 milliseconds with the device is already off, triggers the TRIAC once, and leave the interrupt procedure back to the endless loop waiting for the next interrupt on 0.Z3. Just as in the first half wave, the device works for only 6 milliseconds in the second half wave, and this is what will happen in all subsequent half waves. The device now is on for 6 milliseconds, and off for 4 milliseconds in each half wave. Let's ignore the device's off time. This is the operating time of the AC current wave in our example. We can change the on-off time of the device by changing the delay time of the TRIAC triggering in the interrupt procedure. Of course, the longer the on time, the higher the power, and vice versa. This is the method of controlling the power of electrical devices using the TRIAC driven by the electronic microcontroller. This method is called phase control. Let us now ask the following question. What is the actual voltage applied to the device in this example? Since the device operates for 6 milliseconds of a total half wave length of 10 milliseconds, we may guess that the voltage applied to the device is 60% of the supply voltage, which means 60% of 220 volts, or 132 volts. In fact, this answer is wrong. The reason is that the AC wave is sinusoidal and not linear, that is, the relationship between the output voltage and the triggering angle, alpha, is not linear. The actual voltage applied to the device is called VRMS. VRMS stands for root mean square voltage. It is the effective voltage of a sine wave. It is calculated by the following equation. In this equation, Vs is the supply voltage, 220 volts. Alpha is the triggering angle that must be calculated to derive the value of VRMS. The full sine wave path can be represented by a circular path as in figure. The triggering angle is the angle of the point at which the TRIAC was triggered, referred to as alpha. It is calculated by the formula alpha equals Wt, where W equals 2 pi f. Pi equals 3.14. F is the frequency, 50 Hz. T is the triggering time, which is 4 milliseconds in our example. By substitution in the equation, alpha equals 0.4 pi. We can now calculate the actual voltage, VRMS, by substituting in VRMS equation mentioned earlier. The result is that the voltage, VRMS equals 183.2 volts, it is the actual voltage applied to the device, when it runs for just 6 milliseconds per the half wave. Once the value of the voltage VRMS is known, the device's power can be easily calculated using the power equation. The power equal to the square of the voltage VRMS, divided by the resistance of the device, assuming that the resistance of the device is constant. This is a printed circuit board diagram of a power control device, which has been studied, designed, and tested, based on the information of this research. The circuit is designed in two parts to reduce the area of the casing in which it will be installed. The first part contains the 220-volt power supply socket, the device connector socket, the OPTOISOLATOR, MOC3023, the optocoupler, 4N28, and the TRIAC. The TRIAC BTA16 is used for devices with a maximum current of 16 amperes. For devices with higher currents up to 40 amperes, the TRIAC BTA40 can be used instead. The second part contains mainly the electronic microcontrollers, an LCD screen to display the data. This circuit controls the device's power within 16 levels, from 10% to 100%, with an increment step of 6%. The current power level is shown digitally on the screen, and visually on 16 LEDs at the front of the board. In addition to the power control process, an optional timer is also supported in the circuit, that can be easily adjusted, to automatically disconnect the device after a specified operating period, up to 24 hours. A specific power level can be saved, so that the device works at this level immediately as soon as it turns on later. It is also possible to save, erase, and modify the timer information. The next video contains a detailed description about this device. Thanks for watching. Good luck.